Okay, welcome everyone. I would like to welcome you to this presentation or this webinar. This is our last webinar before we make a break in the summer, in the European summer holidays. So today's topic is the unsaturated flow modeling. Infiltration processes is basically an introduction of modeling unsaturated flow using FEFLOW. So I would like to give you a few hints how to get started with this unsaturated flow modeling with FEFLOW. So it's mainly an introductory webinar for this. And the agenda today will be a short presentation about the capabilities of the software and what is actually unsaturated modeling. Then we will have a quick demo exercise, also very simple. So for those who are really new to FEFLOW or it's the first time that you are participated in this webinar. So we have a set of different webinars covering different topics of groundwater modeling. So we are basically here. In DHI, there are also other softwares related to multiple aspects of the water cycle. There are also different webinars in different topics. So if you are interested, I recommend you to look in our Academy website. So FEFLOW is an old software. It's capable to simulate groundwater flow processes involving also contaminant transport, age, heat transport under fully and variable saturated conditions. So the term of variable saturated conditions is what we are gonna discuss today. It's not a new software. It's a very old, exists in the late 70s. It's being developed continuously by DHI. We have 2 releases per year. We just released one update 2 of FEFLOW A0 a few weeks ago, and we will have a major release later November this year. So we are currently in version A0. If you haven't installed A0, you're still working with the old version. There are 4 major reasons why to use A0. So we start expanding our workflows for conceptual modeling. So we have changed the way how we build meshes from 2D to 3D, and material properties and few things can be also implemented in the super mesh stage. We introduce new technologies to repair meshes. So if you work with 3D data or geological data, you can download this data and import it in FEFLOW. If the data is not 100% clean, you could repair it now within FEFLOW. We have a new well manager editor, which was published last November and has been extended in this last release with a Python interface. And for those working in the geothermal market, we have a number of improvements coming now in November. So we will have the possibility to implement open loop systems and closed loop systems directly from the well manager. And the fourth option is the MyCloud execution for FEFLOW and the FIPS graphical interface. So where you can deploy your FEFLOW runs or FIPS projects directly to the DHI cloud without leaving the graphical interface. So we try to establish all these different processes. So today we will be talking about unsaturated flow modeling or variable saturated conditions. And we keep using always this concept of all-in-one solution. So for you, when you decide to start working with the so-called Richards equation, basically means to activate a couple of clicks or checkboxes to say, I would like to work with this. So one of our major courses also boosts efficiency and saving time. So we have been developing a number of methods to speed up workflows, but also to allow users to interact with the software through the programming interface. And we have been putting a lot of attention about the visualizations. Also, I like to say things that come. So it's gonna come in November, another 3D visualization. So we will support extended visualization for an structure mesh. So we will bring something called orthogonal view, where you will have the easily possibility to display 3D objects or 3D meshes and clip it with some sliders so that you can nicely see what is happening inside. So I will go quickly to this because it's a general part. So FEFLOW has a number of techniques and meshes numerical methods. When we talk later about unsaturated flow, we can see the benefit of these numerical methods. Come with a PES interface, professional interface, also a flexible user interface, and comes with a number of soft information like premium technical support or academy. Like today webinar, we have a number of materials available for you for free or on demand training courses, which will help you to different aspects of the modeling workflow. And we try to bring everything in one interface, one file, one project, and having one single software for the entire workflow from concept, mesh, setting, simulation, calibration, and prediction. Okay, so let's jump into the topic, into today's presentation is unsaturated flow. So you might have seen some of these slides if you have been in the past in training courses or in FEFLOW webinars. So these are few slides which are very useful to explain, come to the topic. So one typical example is of unsaturated flow is dam seepage. So we would like to estimate seepage in a specific structure. So where is actually the seepage taking place? So what is the pressure distribution? What is the saturation? So these are the results of the simulation. And here we might have multiple materials, we might have different heterogeneity. So it's really needed to work with unsaturated parameter or saturated flow model types here to capture all these different heterogeneities. Other cases where it's needed to work with the Richards equation is underground sites or underground constructions or excavations, tunnels, or this example of a gas gallery. So there are seepages happening, so it might be interesting to estimate pressure distributions and others. So this is where it's recommended to use Richards equations. Or other cases of mining applications, if you see infiltration processes, so you see the walls of the pit mine or the pit shell, so there will be infiltration. Maybe there are some drainages, maybe you have some recharge on top which is infiltrating, so you would like to model these processes in the unsaturated zone in order to better estimate your pressure distributions or the seepage calculations. So when we talk about this unsaturated flow, so we say, okay, unsaturated flow, if we remember our hydrogeological classes, so we used to explain this with three phases: soil, a solid, a gas, so a void space, and a fill space with water. So we talk about multiple, let's call it compartments to explain it simple. But we don't want to simulate this compartment separately because we'll be basically overkilling the numerical calculation. Will take more time to do in multi-phases. So we simplify this by having one single phase. So FEFLOW is one single phase. So we talk about gas, we talk about water, we talk about unsaturated porous media, which is gas, the rest, but we're still working in one single phase. So why do we care about this? Because if we have saturated media, it makes a difference in terms of the unsaturated media, because in the unsaturated field we might have this connection of different flow fields, because maybe the porous media is partially unsaturated. So we typically talk about different paths, how the flow goes. So this is normally called tortuosity. Such a processes are obviously relevant because it's not going to be the same flow field that we see in a saturated system. So what we are solving behind the scenes is this famous Richards equation. Is not news. It's the publication, if I remember correctly, is from the 1930s or 33. So in that time, so it was proposed that the system, so the relationship between hydraulic head or pressure head is C, could be related to saturation, and that the way how the fluid move in the unsaturated system depends on the conductivity, and this conductivity is not anymore the saturated hydraulic conductivity, now becomes a conductivity function which depends on the current saturation. So all this interconnection of parametrics makes difficult to solve. So this what we name here as nonlinearity, because there is a connection between the pressure heads and the saturation, and there is a connection again between the saturation and the conductivity. So if we apply this equation to a, or if we change the media from an unsaturated system to a saturated system, basically this term here will become 1. And so this is 1, and this you have saturated hydraulic conductivity multiplied by a hydraulic gradient, which we know, and this becomes basically analog to Darcy law. And this S as a function of the pressure head becomes 1, basically. So the equation describes the water phase with different constitutive relationships. We also identify there is a relative conductivity applied here, and the equation is valid for saturated and unsaturated conditions. So this equation comes as many with some assumptions or simplifications. So the major assumption is that we reduce the problem to a single phase. So what we were saying before, so we don't need to separate the calculations of gas phase and fluid phase. So we treated everything as a one single phase, which has a major benefits to be computational efficient, and also is valid, as we were saying, for the both saturated and unsaturated zone. So there are 3 ways how to formulate this equation. So if you have been working with FEFLOW, with the unsaturated problem class, with the Richland problem class, you will see there are 3 formulations. I try to put here few, let's say, details, or they're not really conditions, they are details of when to apply the equations, or in which cases they are valid. You can also have more details if you're interested on those, how the equation looks like, or how the equation changed from the standard form to the mixed form, or the S-based or saturation-based form. You can look into the FEFLOW white papers or the FEFLOW book. So the default option in FEFLOW is called standard form, which is a pressure head base or hydraulic head base, could be, so P or the H base standard. It's applicable for unsaturated and saturated conditions, and it works for heterogeneous porous media. This is the default option. And your second alternative, if this option, let's say, fail because of the complexity of your problem settings, is to work with what we call natural form, which is the mix form between H and saturation. So head and saturation. Why we have here why we need a change. So in the first form here, we solve as a process variables, as the key parameter to be solved is head. In the mixed form, FEFLOW make a swap of these variables depending on the needs. Solve as a process variable, as a major primary variable head, or solve as a saturation, depending whether one or the other approach fail. It will just swap conditions. And this is also applicable for heterogeneous porous media and both saturated and unsaturated conditions. There is another formulation what is less used, but it exists. It's very efficient, but one needs to be careful to use it. It's basically recommended for dry conditions and for homogeneous porous media, and only under unsaturated conditions. So if you imagine that you are simulating a big zone which is unsaturated, and the water table maybe is just the bottom of your model domain, or maybe not even in the domain, you are doing a column experiment or a simple estimation, kind of a 1D estimation, then you can go for this system if it fulfill these different conditions. Sorry. Okay, so we were looking the equation, and then we see that there is a number of parameters that we need to that we require in order to solve it. And I will show you these options in the FEFLOW during the FEFLOW demonstration. So these parameters or these relations can be expressed in multiple ways. So these parameters or these expressions are non-linear. They can be include some terms or some methods or mechanisms named hysteresis, which I will explain later. So the relationship or these constitutive relationships are two. The first one is what we typically is calling every soil physics or hydrogeological book is a retention curve, so soil water retention curve, which typically draws moisture content or saturation. Is actually used in FEFLOW. The saturation in FEFLOW is from something close to zero. It cannot be zero, and 1. So 1 means that the system, the porous media, is the total porosity is occupied, is fulfilled with water, and pressure and negative pressure. So we reduce the pressure, we drain the system, we dewater the system, the saturation decrease. In the second case, we have a relationship between the conductivity, the relative conductivity factors is a factor which goes to 1 to something close to 0. It cannot be 0 because solvers and numerical methods, they don't like to work with 0 tensors. So we have an increase of saturation. We tend to have the maximum relative conductivity. So this will be a 1. Therefore, this becomes at the end the saturated hydraulic conductivity. Okay, so how do we express these equations? There are many methods, many empirical models. These empirical models are not new. They have been developed since many years. There are tons of publications about these models with FEFLOW, without FEFLOW, with laboratory experiments, field data, etc. There are many softwares which base on this method. So the most famous are, if I might say here, is Bangenuchten modified and Brutz and Corey. So, but Bangenuchte is by far one of the most popular use. So you could choose in FEFLOW basically the model. How do you want to represent your parameters, your unsaturated flow, and then depending on the model, FEFLOW requires a number of parameters, and we are going to see these parameters later. Other formulation is what we name here parametric functions. Parametric functions, in simple words, means polynomial fit. So you got some data, and then you put this data in this little a small graphical interface, so pressure, head, and saturation, and then you ask FEFLOW to make a fit. So this is not something which is normally used because sampling these soil retention curves is not a common task. So I used to do this many years ago, and for that you need soil cores, which collects a small volume. Then you apply the sample certain vacuum, and then you start drainaging and measuring the pressure and the saturation. So you can come out with soil retention. So normally, let's say regional hydrogeological studies, they do not collect such a data. So basically, most of the parametrization are based on either literature values or some manual adjustment done by calibration or expert knowledge. So we talk about these different retention curves. So bringing the very basic of this comes, or the whole concept of Bangenuchten or Richards comes from soil physics. So you normally will find here, I actually forgot to put the literature, the reference, the source of the literature. So normally find typical curves for soils, for sand, sandy soil, silt, loam, clay, or a combination of these. And here there is example of multiple retention curves. Be careful here, this retention curve is slightly different to what you see in FEFLOW, because here shows volumetric water content. So it's a volume of water divided by a total volume of the the domain of the soil, and FEFLOW is a scale from 0 to 1 because we divided this by the porosity. And here you have a matrix potential, or it's also called pressure heads. So you see decrease, so increase of pressure, we have basically a system which is highly saturated, or tends to be highly saturated. There are different databases, so I thought will be interesting for some of you. I mean, so normally we have very international audits, so there are databases where you can get these parameters, so there are, depending on the country where you are, it might be different databases. So I brought this, it's called Unsaturated United States Soil Database. That's the reference, Lake 1996. So which has sampled or has collected or compiled a number of studies of different samples around this United States, and then this data is available for different soils. You can use this information as reference. Other ways to get these parameters are what they are called pedotransfer functions for soil unsaturated parameters. There are many of these. These equations also change depending geographies. If you I see many in Germany. So in Germany, for example, I know some publications from the UFZ in Leipzig who has done some studies on this. So there are also some functions depending on soil, on sand percentage, and bulk density or organic matter. So these are the typical parameters. And these functions, so they were derived by samples, and then you applying these samples to some statistical methods to come out with empirical function. Okay, so there are few ways to get this data. So other concept that is not much used in FEFLOW, but is also available, is the possibility to apply what is called hysteresis. So this is this basically try to say that so if you drainage a system, so you have a column with soil and you drainage, then you have a retention curve. And if the soil is dry and then you start saturated from the bottom or from the top, then not necessarily is gonna have, it's gonna take the same path. So it's gonna drive to another retention curve. So this effect is called hysteresis and can be modeled in FEFLOW by following this Scott method. There are some special boundary conditions that are available with this unsaturated problem. The most common is called seepage phase boundary condition, and it's something that I'm going to use. So it's used to estimate, as the name saying, seepages. There is a second boundary that is, I don't have the slides here. It's called free drainage, which is used for simulating outflowing conditions from the bottom of your models in case the water table is far away from the end of your model domain. Okay, so with this, I would like to jump to a quick live demonstration. So I will start opening FEFLOW A0. So I make something simple because we don't have much time, and we also don't want to wait a lot for the calculation. So we want to use the time for testing multiple things. So the whole idea of this is, I mean, you see, it's a simple cross section. I have 10 meters thickness of the layer, and there is a pool, I call this, but this could be a pond, or could be maybe a artificial recharge zone, or could be some tailing facility. So it has it could store some water here. So we can add a boundary to set some water. So what we want to do basically is, so we want to simulate first the conditions without seepage, and in a second state conditions with seepage. So we want to put some general heads left and right, and then see how much is leaving. We would like to also see what is happening if we change the different parameters. So how to change these parameters, or how to define these different formulations, the 3 different formulations of Rachel's equation. So we're going to look on this. So a few things were already prepared to save some time. You see here, so this is basically the location where I'm gonna put my boundary condition. I have created like a parallel set of lines because I would like to use in the mesh generator the possibility to have more elements. So why do we need this? I mean, now I come to the different tips of what you basically require to succeed with these models. So normally these problems with unsaturated flow are hard to solve. That's the first message. So you can avoid to get stuck in these complexities by having a proper mesh and also by having a model which is well refined. So here I know that if I imagine that the water level is high and this is a hole, a trench, and I would like to simulate the discharge here. So I presumable I will have quite high velocities in the interface of these vertical walls on the base of the trench. So for that reason, I would like to have a quite well refined. So there might be a depression cone, which we don't know, depends on the hydraulic parameters, so might be very far away from the area of the trench, maybe is closer. So I would also like to have another zone here with the medium-sized elements. And for this, we use the, going quick here, some specific mesh density factor, so 10 and 25. Then I have some gradations of the lines. I want to change the size of the elements gradually so we can generate a mesh out of that. So let's generate a mesh, and it's that. So having this mesh, so normally what you will do is to do some smooth operations. So I will skip it because of the time, and let's put some boundary conditions. So let's make it 1, and then I will open the file so that we can just say sometimes. So here on the left side, I will say that the head is close to the elevation stem, so it's touching the topography, and on the other side, it will be basically a little bit lower. So make it 9 or 9.5. Let's put 9.5. So I make a mistake now, and the mistake is because after I generate a mesh, I haven't tell FEFLOW what I suppose or what I want to do, and for this you use the problem setting. So we should have done this actually before, because if you see FEFLOW thinks that it's a 2D model. So let's go to vertical Richer. Here is the way how you use the Richer's equation, you apply. And somebody was asking me in the chat, Thomas, how to set this auction. So you see here, we have a tab called Unsaturated Flow, and you have the 3 different auctions: head, mixed, and variable substitution. So this is the auctions, the location where you switch between the different formulations of the Richer's equation. Okay, so you also have a number of parameters here, which I'm going to explain later at the end of the exercise. So for this, you also see FEFLOW set as default transient, especially for the Richer's equation, because it's hard to solve it. It's easy to solve it in transient. So if you would like to test a steady state, so you can do it. Sometimes it might fail because depends on the complexity of your boundary conditions on the model. In this very simple case where there is just a head on the left and on the right side, there is obviously a lot of good chances that we can solve the system. So if we just run it, and I wouldn't save it, and then I have obviously a distribution of head and a distribution of pressure. Since we are basically now also solving for other parameters like saturation, they will be also available. So I haven't changed anything, and just FEFLOW give me some distribution of parameter, saturation, and moisture content. So look on this saturation here, and at the same time, I'm gonna put what we call the pressure, the zero ISO line. So I see there are some areas in, so my major part of the domain is red, so it's fully saturated with 1. Other areas are in between. So I didn't have a special refinement in the top, so I might be maybe good to have some finer discretization here. So this is what we start, but let's start making the model a bit more realistic. So for this, I wanna load the model that I prepared. Here, let's put this one, what we call seepage. Is basically the same model, but this time we tell the software that we would like to open this boundary here. So we like to simulate air pressure conditions with seepage phase, and if we run this, we are going to see that the water level decrease immediately to the location of this. In this location, there is no head, no positive pressure, so FEFLOW switch the boundary to a well visit to an off-flow boundary and only keeps the hydraulic heads here. So let's look this is the hydraulic head. So we have it. Let's look the saturation now. And now the saturation looks a little bit bumpy. So we have some, let's say, smooth gradations of saturation and in the area close to the trench because of the refinement, but in the other location is like so something which is not that good. So I might need here to improve the discretizations. Why is also important if we now, let's say, go to this auxiliary data, there is a parameter that is not much known, but it's really very practical. So you can use it every time and even before you run the simulation in case you would like to check your parameters. If you look for relative permeability, basically this relative permeability, if we come back to the equation, is this Kr. Is the current value of Kr depending on the value of S of saturation. So what is telling me that I haven't changed anything. So no parameters in FEFLOW were changed, just using default parameters. Is FEFLOW use provide for this level of saturation, which we saw before. So basically this part of the model is dry. It calculates a value of 10 to the minus 5 dimensionless. So it means 10 to the minus 5 multiplied by the value of conductivity. So I haven't changed also any value of conductivity. If I double click conductivity max, I see my default value is 1. So this 1 times 10 to the minus 5 basically is the value, the current value to be used in all these different elements for the nodes. So now let's imagine, okay, we have these elements quite coarse. Maybe my relative permeability here is something about 0.5. Maybe the real value is not at 0.5, maybe it's less because depends on the discretization that I have. And since I only have one triangle, so FEFLOW is not, obviously cannot do more than that. So the obvious condition here will be to improve the refinement. So let's load another file where we have, I call it base. And this file was very simple done. So it's the same file. I just pick a box or a square, select the area that I want and refine. Normally you would do that if it's possible in the super mesh, so you avoid to have these different this zigzag on the discretization. But this is an example test for demonstration, so it's good. Right, so we have now the better discretization. So let's try to run the model again and then see what's happening. So if I plot the hydraulic heads, it takes a little bit more time because of the increase of the number of nodes, but still we are in a second scale. So if we go to the relative permeability, so now we can indeed see that most of the conductivity, the relative permeability has been accommodated better to the finer elements. So look, and we have also a very smooth transition here. So let us start doing something more interesting. So what normally would have is you have different materials here, different soil parameters. So let's include this in the calculation and see what comes out. So let me look here with the Ray budget panel. So far, I would like to see what is the seepage. So I have a seepage. So we have a selection called seepage, which is this border, and FEFLOW is telling me that there is outflow 0.6 negative cubic meters per day. Good. So let's change the parameters, and I have also prepared the same file, but this time with different parameters. Again, it's something that you can do in your own time, but there is no much time to go through the all of this stuff. So I have changed the conductivity. So I am assuming everywhere is a sandy soil, so it's a very high conductivity. So 0.64 meters per day. We can switch it to meters per second that we see. So it's meters per second, and here I have I try to simulate some barriers. So let's say I have some clay materials, or maybe even something less permeable than clay use. Could be some geotechnical structure that we are trying to implement, maybe some sheet piles here. So we have this 10 to the minus 6 meters per second in this area. So what I call here barriers. They're just basically blocks. What else? So now we start looking in the unsaturated parameters. Let me close this. You see here there is something called unsaturated flow porosity. I haven't changed it, so actually I forgot to change. I should have changed it. And there is a question in the chat, so which I will use now to answer it. The unsaturated flow porosity in FEFLOW is actually the total porosity. Yes, it is actually the total porosity. So here you will have a porosity for the sand, well, let's say 0.335, and for clay, the total porosity for clay will be even higher, so 0.4, 0.445 in some cases. Yeah. Then beside the conductivity and the porosity, you need a model. We have the different models to simulate this. So the default is Van Genuchten. So you don't know what is actually Van Genuchten using. So the best way is just go to the name of the model, move your mouse over the name, and FEFLOW will bring this tooltip with a set of two equations. So the first one describes the connection between the relative saturation, SE, and the pressure head. So you see a little bit, looks a bit complex. So there are two conditions. So the first one is, I cannot move the mouse to show you. The first one is if the pressure head is 0 or greater than 0. So it's actually 1. Saturation is 1. Unsaturated conditions. If the pressure head is less than 0, so we apply the equation. The second equation is for the conductivity Kr related to the SE with a power of 0.5 and a number of factors. These equations depend on some empirical parameters, so M, N, alpha. Some of these parameters, they have a physical meaning, others they are empirical. The first one, if we look Van Genuchten, I have changed the alpha because the alpha represents the inverse of the capillary fringe. So if we try to remember our soil classes, so if we try to, let's say, if we look what is happening in the interface between the saturated and unsaturated zone, so there are some capillary pressures that will make to rise a little bit. In simple words, saying the water column on this interface, and these heights or this capillary height change depending on the distribution of the grains. And since because we have sand and clay, there might be some clear difference. Then we have also M parameter, which is also different, and this depends again in some material property in soil types. So I haven't changed anything else, and now what I'm gonna do is to show the saturation. So let's remove let's put actually the pressure head is 0. So I didn't calculate anything in FEFLOW. And if we run it, so it's gonna take again a few seconds. You see it's running now PCG. That is also not good. I mean, I could have used a parallel solver to save another few seconds, but that's enough. So that's the distribution now of the head. It looks a bit different So for now, we ignore head because I want to show you basically saturation, which is the parameter with normally we don't look in standard groundwater projects. So here you have the two zones. So if I plot on top the selection of the barriers coincide, this means that here the effect that I see, so this rise of the saturation. So my water table is the white lines. The capillary fringe is basically the zone of elements which is in reddish. And this reddish color, or red is the transition between red and orange, change a little bit here in the well, not a little bit, significantly in the case of the clay material, because we are telling FEFLOW that the capillary zone is basically slightly higher in clay compared to sand. So it's increase of the saturation. Okay, so how it does affect the typical parameter if we do groundwater modeling, the conductivity. We like to work with conductivity. So let's look the relative permeability, and then we can see that there is a partially change on the relative conductivity. So if the soil is more saturated, the conductivity, the relative permeability will be also slightly higher than if the soil is completely dry. So we have also some changes. In this model probably does not make a big difference, but if you imagine to put some recharge on the top of the model, on the upper border, so you are basically will expect higher velocities in this block compared to the one here on the left, on to the right. So if we look now, by the way, velocities, we look now distribution of the, put back the saturation, I will lock this. And if we look now the distribution of the Darcy flux nodals, so it's a lot of data. Let's change some colors, Darcy flux, double click. And if we choose logarithmic scale and then double click again and make this a little bit bigger. So we can, I will try to maybe deactivate this, not so, and we need some reference here. So we put the selection here. So you can see, let's look here the trend. So basically it's a lot of outflow, well, or the higher velocity. So the scale is 4.5 meters per day, and the lower is 9, 10 to the minus 6 meters per day. So we are simulating 2D vertical. FEFLOW requires a thickness which is just 1 meter. This means that the velocities that you see are velocities in the average of 1 meter cross-sectional thickness. So we have here the higher velocities coming here. This boundary, remember, is deactivated. It's becoming a no-flow in case of the seepage. This might be questionable, so you can argue about that. If you want, you can ask me this and we can discuss it later in the chat. So we see as well that there is the zone which we use as a barrier here with a low conductivity material. So some of the vectors will just go down. If you see, I hope you can see, go down, and then we'll try to move below the barrier and then rise again and discharge through the open boundary here. Difference also, so if it's your first time working with unsaturated models, so FEFLOW, it's a finite element system, so it solves in each of the FEFLOW nodes a solution of head, pressure, saturation, and moisture content. So this means that there will be flow. So we want to see flow in the unsaturated zone. This is the reason why we are simulating this. So you still see a little flow in the unsaturated zone, but the velocity is small compared to the saturated part. So we are not deactivating any elements if there is a reduction of the saturation as is done in other softwares. So we calculate in every single location. So yes, we are planning more sessions. As I was mentioned, so there will be a break the next month, but we are gonna have a number of sessions from August until December. So we are currently updating this. So the next week latest, you will see all the sessions. So for now, I can tell you that in August, we have a session about mining. So if you are in the mining business or mining consultant, so I would recommend you to come this. We have a topic of geothermal modeling in September here. So this is 1 hour webinar about from shallow to deep geothermal. So we're going to discuss this. And the next appointments will be listed in the coming days. With this, I would like to thank you for participating in this webinar, and I hope to see you in the next coming webinars in August and the rest of the months. Thank you, and until the next time.